So as we transition from looking at the big picture view to looking at the close-up view, oops. Hang on. Right. So as we make that transition, you'll notice that a lot of the polynomials are given in a factored form, and there's a good reason for that. When we do our close-up analysis, this will actually make our life a lot simpler. But let's make sure that we don't lose track of the big picture because the form has changed. Remember that the behavior of this polynomial from the 30,000 foot view, in other words, as x is going to infinity or minus infinity, that behavior is the same as the behavior of its highest degree term. So when we see something like this, I want you to realize that we do know the highest degree term from this. Let me just rewrite it real quick without that square in there. So don't forget, when we are squaring something, that's really just multiplying it in there twice. Right, so that's what the squaring x minus 1 squared means. So what we know from the distributive property is that when we multiply polynomials, that the multiplication basically chooses one of each thing that's in the, for each of the terms, it chooses one of those terms to multiply together. So we're going to take one of x minus x and minus 3, take one of x and plus 4, take one of x and minus 1, take one of x and minus 1, and multiply them together. And then we do that in all possible ways, with all possible choices. So you'd get lots of terms if you did that. We don't need all the terms, we just need the highest degree term. And it's pretty obvious if you think about how, if that's what the distributive property is telling you to do, then the highest degree term you're going to get is if in every parentheses where you have a choice about which thing to take, you take the one with the x. So in the distributive property, it would multiply the minus 2 times the x times the x times the x times the x. That's just one of 16 different terms you could get for this. And don't worry about where the number 16 goes. We're not going to ever generate all 16 of these terms. But that's the only one that has 4 x's in it. And so this polynomial is going to have a term that's minus 2 times x to the 4th. That's the product of all the ones I underline. And then it's going to be plus a bunch of other stuff. And all the other stuff definitely doesn't use 4 x's. So the minus 2x to the 4th is the highest degree term. And so I know from that from the 30,000 foot view, the graph of this polynomial looks like the graph of y equals minus 2x to the 4th. And so that's what I've shown you here on the graph. Y equals minus 2x to the 4th is just this orange looking graph. And the graph of the original is this blue graph. And so you can see that once again out here at the ends, those graphs are similar. They're going in the same direction. And just like before, all bets are off about what's going on in here. We got some wiggling going on and stuff. So we're not suggesting that these two things are the same in here, but we are saying that they behave the same way out at the ends. So in this case, we would say as x goes to infinity, meaning x is going out to the right, y should be going to minus infinity, and as x goes out to the left, the y also goes down. So that's how we could express the shape of this polynomial. Okay, so what do we want to do with that stuff in the middle? Well, the first thing we're going to do is just pick up on something that we were doing before, which is the horizontal and vertical intercepts. That is part of the behavior of the graph in the middle of it where it's wiggling around. So the vertical intercept, remember, a vertical intercept comes from, well, a vertical intercept is a point of the form 0, comma something. And so to figure out what that something is, I just have to evaluate h of 0. So if I know the input should be 0, then the output is just going to be h of 0. So to do that, I'm just putting 0 in for x. And if you need a calculator to do that, that's perfectly fine, and you'll get 24. So the vertical intercept is the point 0, 24, and I have already drawn the picture over here, so that's that point right there, 0, comma 24. The horizontal intercepts are always harder, at least when things are described algebraically, because we are trying to find x so that the output is 0. Now remember the formula for the function, the formula up here, the formula up here, that is a formula for the outputs. That's what that is. So I'm trying to find an x so that minus 2 times x minus 3 times x plus 4. Right? So that's the formula for the outputs. I want that to be equal to 0. So I'm literally saying here, find the input so that the output is 0. This is why we have the polynomial described in factored form. Remember, our procedure for solving a polynomial equation is first get everything on one side and 0 on the other. This already has that going on. The second step is try to rewrite the left-hand side as a product of things rather than a sum of things. And because of the form we got this in, that's already done. So in that process, that's three-step process of solving polynomial equations, the first two steps have already been done for us. And so the conclusion, when we have it to this point, is that one of these terms has to be 0. I don't know which one, but one of these three things that are multiplied together here has to be 0. Notice that I'm ignoring the square on that because if you think about it, the squaring is not going to change what number makes it 0. 0 squared, 0 cubed, 0 to the fourth, right? 0 to a power is just 0. So the only way for the x minus 1 squared term to be 0 is if x minus 1 is 0. So that gives us three possibilities, and each of those is an easy equation to solve. The x minus 3 is 0 when x is 3. X plus 4 is 0 when x is minus 4. And x minus 1 is 0 when x is 1. So that would give me x equals 1, x equals 3, and x equals minus 4. So those are my three horizontal intercepts. So minus 4, 0, 1, 0, and 3, 0. All right, so you should try the next one, and then I'll write the answers in. All right, so I've written in my answers doing the same two things. In the first case, I'm putting 0 as my input and 12 as the output, so that gives me the point 0, 12, which I plotted. In the second case, I'm setting the formula for outputs equal to 0. That's how I'm going to make my output equal to 0. And then I'm finding the inputs x that'll make that happen. And I've found that when x is 1 or negative 3 or 2, then those inputs make me have an output of 0. So I would plot those as well. This would be the point negative 3, 0. This would be the point 1, 0. And this is the point 2, 0. So those are all of my horizontal intercepts. Just FYI, when there's not a graph around, calling those things horizontal intercepts seems weird if you're not graphing them. So in the world of functions, we have a different name for that. So when you have a horizontal intercept on the graph, so these numbers like x equals 1, x equals minus 3, x equals 2, when there's not a graph lying around, we call those, we say those are zeros of the function. So a 0 of the function is an input that makes your output 0. And so you'll see that that terminology used, especially in problems where there's no graph in sight, where you're not trying to draw a graph. That's not the point of the problem. You'll see references to zeros of a function, and so that just means inputs that make the output 0, and it is exactly the same algebraically as finding horizontal intercepts. It's just it doesn't make sense to call something a horizontal intercept when there's no graph around.